In this video, we will talk about a third method of numerical integration known as Simpson's rule. Simpson's rule is based on the idea that we can use a degree 2 polynomial, a quadratic function, to estimate the behavior of a curve on an interval. And if that seems weird, consider what we talked about with the midpoint rule and the trapezoid rule. In each of these, we have a base sitting on the x-axis, and then two lines that are perpendicular to it, extending up the left side of the subinterval and the right side of the subinterval. Now, how high they go was based on whether we were doing rectangles or trapezoids. So if we were doing a rectangle based on the midpoint, we would find the y value of the function at the midpoint of the interval and then draw a horizontal line through that, thus forming a rectangle because the horizontal line at the top was parallel to the axis at the bottom. And then we had the two perpendicular sides making a rectangle that were both the same height. So we had a horizontal line governing the top of the subinterval. In the trapezoid rule, we used a diagonal line. We allowed the left side to extend all the way up to the function, and the right side to extend all the way up to the function, which of course might be at two different y values. And thus, when we connected those 2 points, we had a diagonal line, also known as a degree 1 polynomial. The horizontal line that governed the top of the rectangle in the midpoint rule, it could also be thought of as a degree 0 polynomial. So we went from a rectangle using a degree 0 polynomial at the top to a trapezoid using a degree 1 polynomial at the top. The next logical extension of that would be to use a degree 2 polynomial at the top. The degree 2 polynomial should be a better estimation of the behavior of the curve, in general, a better estimation of the behavior of the curve than the degree 1, which was better than the degree 0. Now, in order to do this, we need to establish some algebra first. It is necessary to show that for any second degree polynomial function, which would be defined as big A times x squared plus big B times x plus big C. In that case, the integral from little a to little b of this polynomial is actually going to be equal to the width of the interval divided by 6 times the polynomial evaluated at the left endpoint plus 4 times the polynomial evaluated at the midpoint of the interval plus the polynomial evaluated at the right endpoint of the interval. Now this is quite the claim, definitely less than obvious. So we're going to go through the algebra to prove this. This is a direct proof and simply requires the algebra to work with. Now, the reason why we have unspecified values for big A, big B, and big C is that every parabola is defined by those 3 parameters, and they're going to be different for each parabola. So even if we move from one subinterval to the next, that horizontal shifting would result in different values for A, B, and C, to say nothing of the fact that the parabola now has to pass through potentially different points with different y values as well as different x values. So those capital A, capital B, and capital C values will change from one parabola to the next. What we're saying then is that whatever that parabola turns out to be, we can evaluate the integral using only the little a and little b without actually having to establish the values of big A, big B, and big C. So what we're going to start with is that we have the integral from little a to little b of our polynomial. which we can then rewrite this integral using the generic form big A times x squared plus big B times x plus big C dx. And the entire purpose of this algebra is going to be to show that we never actually need to determine the exact values of big A, big B, and big C in order to make this work. So, to do a definite integral, we start with the antiderivative, which is easy enough to do. The big A is just a coefficient, so the antiderivative of x squared is x cubed over 3. The big B likewise is just a coefficient, so the antiderivative of x is x squared over 2. And then big C is just a constant, so its antiderivative is linear, big C times x. And this will be evaluated at each of the endpoints, so that we have big A times little b cubed over 3, plus big B times little b squared over 2, plus C times little b. And then subtracted from that is big A times little a cubed over 3, plus big B times little a squared over 2, plus big C times little a. Rearranging these terms to put the capital letters together means that we can now have big A times b cubed minus a cubed over 3, plus big B times little b squared minus little a squared over 2, plus big C times little b minus little a. We have two things now to do. One is that in order to be able to work with these, because two of them have different denominators, and then the third doesn't have a denominator at all, or rather has a denominator of 1, we need to get a common denominator for all these things. To do that means we need to multiply the first fraction by 2 top and bottom. The second fraction needs to be multiplied by 3 top and bottom. And the third needs to be multiplied by 6 top and bottom. The other thing we need to do is to factor each of those b to a power minus a to a power. B cubed minus a cubed is a difference of cubes and can be factored as little b minus little a times little a squared plus little a times little b plus little b squared. B squared minus a squared is, of course, a difference of squares, which factors as b minus a, little b minus little a, times little b plus little a. And then, of course, the last term doesn't need any factoring at all. But now what we have is that each of these has a factor of b minus a in the top. And actually, they each have a factor of 6 in the denominator. These things can be factored out, thus giving us our b minus a over 6 in front of the whole thing. The remainder of this proof will be in showing that what is left after we factor this out will turn into the second half of our conclusion statement. So at this point, we are factoring out the common b minus a from the numerator and the common 6 from the denominator, which leaves us with 2 times big A times little a squared plus little a times little b plus little b squared, plus 3 times big B times little b plus little a, plus 6c. The obvious thing to do here is to distribute the 2 times big A and the 3 times big B. Which gives us 2 times big A times little a squared, plus 2 times big A times little b, plus 2 times big A times little b squared, plus 3 times big B times little b, plus 3 times big B times little a, plus 6c. Now, ultimately, what we want to have out of this at the end is we would like to have a p of little a, which should be big A times little a squared, which we have. We have two of them, actually, right here. We also want to have a big B times little a, and we, again, have some of those right here. We have 3 of them. And then we want to have a C, which, again, we have several of. We have 6 C's over here. Likewise, as part of our end result, we would like to have a P of little b, which would be big A times little b squared plus big B times little b plus c, each of which we have multiple of in this expression. We also want to have something else in between the P of A and P of B, and we'll deal with that in a moment. Let's first separate out the pieces we need to get P of little a and P of little b. So to get P of little a, we need 1 of our a times little a squareds plus 1 of our big B times little a plus 1 of our c's. At the other end of this, we're going to need, for P of little b, we're going to need 1 of our big A times little b squareds plus 1 of our big B times little b plus 1 of our c's. What that leaves us with in between is the other big A times little a squared, because we had 2 of them. One of them was split off, and the other is left. We didn't touch the 2 times big A times little b, so they're all still there. And we did take 1 of our 2 times big A times little b squareds, but we have the other here. We again took 1 of our big B times little b, which leaves us with 2 big B times little b. We took 1 of our big B times little a's, which leaves us with 2 big B's times little a's left. And we took 2 of our c's, leaving us with 4. So again, these 3 terms are accounted for as P of little a, and these 3 terms are accounted for as P of little b. What we need to do then is show that this is going to become the middle term, P of little a plus b over 2. And that actually isn't all that hard. The first 3 terms share a common big A. So if we factor out that common big A, what we're left with is little a squared plus 2 times little a times little b plus little b squared. To continue to work with this, little a squared plus 2 times little a times little b plus little b squared is a perfect square trinomial. It is a plus b squared. Now, what we're supposed to have is a 4 in front of all of this. In order to make that happen, we can introduce a 4 in front of this as long as we also balance it with a division by 4. Keeping in mind that in the denominator, 4 is just equal to 2 squared. And in that way, we can combine this with the a plus b squared in the top, and this term becomes 4 times big A times little a plus little b over 2 squared. That takes care of the first part. Then we have the terms with the big B. We have a 2 big B times little b plus a 2 big B times little a. And this will be easier to work with since we don't have the exponents on it. We can again factor out the common 2 and the common big B. Now, if we choose, and we will, we can rewrite the little b plus little a as little a plus little b. We can simply reverse the order of it. And in order to get that 4, we just have to multiply this by another 2 and balance it with a division by 2. And, and that gives us 4 times big B times little a plus little b over that denominator of 2. And then, of course, we simply have the 4c. So what we have here are our 3 terms that this simplifies into that all have a 4 in front of them. Together, they're going to simplify down to the 4 factored out times big A times little a plus little b over 2 squared plus big B times little a plus little b over 2 plus big C, which is nothing more than the polynomial evaluated at little a plus little b over 2. And thus, in conclusion, we have our little b minus little a over 6 times 3 terms that turn into p of little a plus 4 times p of little a plus little b over 2 plus p of little b. Now, the purpose of all of this is to show that there is a quadratic function on an interval, and we do not actually need to establish the parameters, the coefficients of that quadratic function in order to know that we can still evaluate the integral on of that quadratic function using nothing more than the endpoints of the interval. Now you might say, but don't I have to plug those endpoints of the interval into the polynomial? So don't I need to know what the polynomial is? Well, actually, no, not when we apply this to an actual function. The next step of this, and a visualization will help here, I'm going to draw a non-quadratic function and we're going to consider it on some interval from a to b. Now, in order for this to work, we need an interval that has a midpoint to it. In order to make our lives a bit easier, I'm going to suggest that we actually consider 2 subintervals at the same time, so that we have x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. And I'm going to suggest that we consider the interval from x sub 0 to x sub 2 as a single subinterval, or a double subinterval, if you will. This then gives us, first of all, the left endpoint x sub 0 and the right endpoint x sub 2. And the midpoint is simply x sub 1, so we don't have to do a more complicated calculation. We essentially will end up with p of x sub 0 plus 4 times p of x sub 1 plus p of x sub 2. And therefore, we remove that complexity of the a plus b over 2 by just using one of our endpoints of our subdivision. Now, what we have from there are 3 points on the function. Three points is the minimum necessary number of points to establish a parabola. In general, the number of points necessary to establish a degree n polynomial is n plus 1 points. Take the midpoint method, for example. In order to establish where to put the horizontal line at the top of the rectangle, we simply need to know 1 point taken from the function. In order to do a diagonal line, a degree 1 polynomial in the trapezoid rule, we needed 2 points. We needed to know the points on the function at the left and right endpoints of the subinterval. So now to do a degree 2 polynomial, we need 3 points taken from the left endpoint of the double subinterval, the midpoint of the double subinterval, and the right endpoint of the double subinterval. And as it turns out, there is a parabola that approximates the behavior of the function on this interval. Now again, it's not perfect, and if you'll forgive the fact that I'm writing on a smooth surface and my hand's a little shaky, it approximates the behavior of this curve. And it does so in a way that might be considered a bit more accurate than 2 separate rectangles or 2 separate trapezoids. Because the curving of the quadratic function is a better approximation of a curving function itself. So what we have here is some polynomial on the interval from x sub 0 to x sub 2. I'm going to call this p sub 1 of x, because we then are going to have to repeat this procedure on the next double subinterval from x sub 2 to x sub 4, where here we're going to have, again, 3 points at the left endpoint of our double subinterval, at the midpoint of our double subinterval, and then at the right endpoint of our double subinterval. And this would be approximated by a parabola that goes something like this, perhaps. Excuse me. This would result in a definite integral from x sub 2 to x sub 4 of some other polynomial function. And the idea is that the sum of these two integrals is going to approximate the area from a to b under the original function. But here's the interesting thing. I said that we don't actually need to define the full function p sub 1 of x or the full function p sub 2 of x, because the points involved in them, remember, as we showed up here, essentially we just need to evaluate that polynomial function at each of the 3 points in question in the subinterval. But p sub x sub 0 is the same thing as f of x sub 0, which means we don't actually need to know the function p sub 1 of x, because we can use f of x to get the value of that point. The same thing here. This point is coincidental to both p sub 1 of x and the original function. So if I don't know p sub 1 of x, I can simply use the original function. So according to this, my area should be approximated by x sub 2 minus x sub 0 over 6 times p sub 1 of x sub 0 plus 4 times p sub 1 of x sub 1 plus p of 1 of x sub 2. For the second integral, then, I have x sub 4 minus x sub 2 over 6 times p sub 2 of x sub 2 plus 4 times p sub 2 of x sub 3 plus p sub 2 of x sub 4. And now a couple of things are going to happen. First, the distance from x sub 0 to x sub 2 is exactly the same as the distance from x sub 2 to x sub 4. So these two fractions are actually equal to each other. If they have the exact same value, then it can be factored out of both of these large terms. That's our first step, is to realize that those two fractions are equal in value, and therefore, instead of writing them with different subscripted x's, we can actually just represent them by the same thing. Now, aside from that, we also, as we said before, said that p sub 1 of x sub 0 is the same as just f of x sub 0. And p sub 1 of x sub 1 is the same as just f of x sub 1. And the same thing is true for p sub 2. P sub 2 of x squared is the same as f of x sub 2. So each of these function notations written with a p sub 1 or a p sub 2 can simply be written with an f. So what we have now, is by factoring out that common fraction, we now essentially have x sub 2 minus x sub 0 over 6 factored out from each of these. And then we're going to have f of x sub 0 plus 4 times f of x sub 1 plus f of x sub 2. That's from the first three terms. And then we're going to have another f of x sub 2 plus 4 times f of x sub 3 plus 1 f of x sub 4. The idea here is much like we saw in the trapezoid rule. The right edge of one double subinterval is going to appear again as the left edge of the next double subinterval. So we get an overlap between them. So while it's the center value of each double subinterval that has a coefficient of 4, the others are going to overlap with each other. And what we have here is x sub 2 minus x sub 0 over 6 times f of x sub 0 plus 4 times f of x sub 1 plus 2 times f of x sub 2 plus 4 times f of x sub 3 plus 1 times f of x sub 4. This would be a formula to give us the approximated area. Now, to give this in a much more generic form, this is known as Simpson's rule, named after the English mathematician Thomas Simpson, who developed this procedure in the early 1700s, in the mid 1700s. As always, we need our function to be continuous on the interval in question. In this case, the integral, the definite integral from a to b of f of x dx can be approximated by the full interval width divided by 3 times n. Now, if you're wondering where the 6 came from, what we essentially had was 2 double subintervals. We had 2 parabolas going on. So 3 times 2 is what gave us the 6 here. And then this is going to be multiplied by f of our first endpoint plus 4 times f of our next endpoint. And then we would have f of our third endpoint. But as we saw before, that's going to overlap because it appears as the right endpoint of the first double subinterval and again as the left endpoint of the next double subinterval. Now, at this point, we have one f of x sub 2 from the first triad, and then another f of x sub 2 as part of the second triad, which means the next thing is the center of that next triad of points. And then we have, again, an f of x sub 4. But if this is continuing with more and more subintervals, then this right endpoint will again be the left endpoint of the next triad, thus giving us 2 of them. Etc. Until the last endpoint of the last subinterval, which, like the very first endpoint of the first subinterval, doesn't have an overlap because there wasn't anything on the other side of it. Same thing here. The interior borders between one double subinterval and the next. The interior ones overlap with each other because there is a subinterval, a double subinterval to the left of x sub 2 and a double subinterval to the right of x sub 2. There is no double subinterval to the left of the beginning, and there is no double subinterval to the right of the end. So what we get is that the coefficients always go in the pattern 1, then 4, then 2, then 4, then 2, then 4, etc. until the end where it drops back to a 1. The coefficients will always follow this pattern. Now, for an example, let's once again take, as we did for both the midpoint and trapezoid rules, let's once again take f of x equals sine of x on 0 to pi. Where, again, we already know that the actual area of this, from the fundamental theorem of calculus, and from having been done in 2 previous videos, we know that this actual area is equal to 2. So let's attempt this with Simpson's rule. And as before, we will start with simply 4 subintervals, or 2 double subintervals. In this case, the area is going to be approximated by the full width of the interval, pi minus 0, over 3 times n, which is 4. And then that's going to be multiplied by sine of 0 plus 4 times sine of pi over 4 plus 2 times sine of pi over 2 plus 4 times sine of 3 pi over 4 plus 1 times sine of pi. So you can see that this actually is not really much more complicated than the trapezoid rule. In fact, really the only difference between this and the trapezoid rule is a minor change in the denominator of that leading fraction, and some of the coefficients are 4s instead of 2s. That's really the only difference, and yet we're going to find that this gives a much more accurate result than the trapezoid rule did, or even the midpoint rule. None of these rules is really that much more complicated than any of the others. There are slight changes to the coefficients involved. There are slight changes to the denominator of the fraction in front, which means in terms of operations that you are performing, the number of operations is actually the same. It's just that some of the values involved have changed. And yet, each of them gives a different degree of accuracy. And in general, Simpson's rule will be the most accurate of them, as we will see as we finish evaluating this. So we have pi over 12. The sine of 0 is 0. The sine of pi over 4 is root 2 over 2. The sine of pi over 2 is 1. The sine of 3 pi over 4 is again root 2 over 2. And the sine of pi is again 0. So through a little bit of cross simplification here, we have 2 root 2 and another 2 root 2 for a total of 4 root 2. And of course, 2 times 1 is 2. So you can see we have some slight differences. When we did this with the trapezoid rule, we had pi over 8, and we had 2 times the square root of 2 plus 2. So some slight changes. A change in the denominator under the pi, and a change in the coefficient in front of the square root of 2. But ultimately, these changes end up giving us a more accurate result. In the trapezoid rule, when n equals 4, our error was off by a little bit more than 0.1. Now our estimate is off by 0.005. Only 5 1/1000ths off from the actual value. That's considerably more accurate. Even the midpoint rule wasn't as accurate as this. We will do it again, as we did with the midpoint and trapezoid rule, with 8 subintervals. So again, our delta x in this case, since it's a little less obvious, we'll go through it. Our delta x is pi minus 0 over 8, or pi over 8. This means that our x sub i's are going to, starting at 0, go up by pi over 8. So we have pi over 8, and then 2 pi over 8, and then 3 pi over 8, 4 pi over 8, 5 pi over 8, 6 pi over 8, 7 pi over 8, and lastly, 8 pi over 8. So, by Simpson's rule, our area is approximated by pi minus 0 over 3 times 8 times sine of 0 plus 4 times sine of pi over 8 plus 2 times sine of pi over 4 plus 4 times sine of 3 pi over 8 plus 2 times sine of pi over 2 plus 4 times sine of 5 pi over 8 plus 2 times sine of 3 pi over 4, plus 4 times sine of 7 pi over 8, plus 1 times sine of pi. Okay, this is large, but again, we're going to be using a calculator, so we can do some cleaning up only to simplify what we're going to put into the calculator, which certainly will help. So first off, our fraction can be written as pi over 24. Second, the terms sine of 0, sine of pi over 4, sine of pi over 2, sine of 3 pi over 4, and sine of pi, we did those previously. Of course, the coefficients have changed slightly. We do still have 2 times sine of pi over 2, but instead of 4 times sine of pi over 4 and 4 times sine of 3 pi over 4, we only have 2 times each of them. So those terms together will end up giving us 2 root 2 plus 2. Now, for the other terms, pi over 8 is symmetric to 7 pi over 8 in that they have the same y value. So those two terms can be combined, and we can call them 8 times sine of pi over 8. Likewise, 3 pi over 8 is symmetric to 5 pi over 8 in that they have the same y-coordinate. So again, those two terms can be combined into 8 times sine of 3 pi over 8. And again, the purpose here is simply to get a simpler expression to have to type into the calculator. We could have just typed the original thing in. It would be very large, very expansive, but this certainly is going to help us get there a little bit more easily. We could go a step further and factor out common factors from these things, but ultimately the idea is simply to get it to a point where we can put it in the calculator and get an accurate value. And as it turns out, this value comes out to be 2.0003, even more accurate than before. With only 8 subintervals, we are now only 3 10,000ths away from the actual value of the area. And that's pretty accurate. Again, much more accurate than either the midpoint rule or the trapezoid rule. It is simply another option that, with some slightly different, slightly larger coefficients in some cases, and a slightly larger denominator underneath in the bottom of that initial fraction, but providing us with noticeably more accuracy despite that. Now again, we've only gone through one single function on one single interval here. And we did it with a function that did not actually require the numerical integration techniques. There are other functions that simply do not work well with algebra. For example, and we're not going to take the time to go through it in this video, but for example, the function sine of x squared. If we were to attempt to do an integral of this, it is a composition. However, the inside function is x squared. Its derivative would be 2x. There is no factor of x in the integrand. So we would run into a problem if we tried to do substitution. You can always attempt integration by parts using u equals the function and dv equals just the dx. And in that way, we could perhaps get away with finding the derivative of sine of x squared rather than its antiderivative. But I think what we would find is that that produces a more difficult integral rather than an easier integral. That being said, we then also have other options like a trigonometric substitution, but unfortunately that's not going to apply here. Trigonometric substitutions always are meant for involving a sum or difference of squares, and depending on the order of them, we might have to go with hyperbolic trigonometric functions rather than circular trigonometric functions. Partial fractions wouldn't even apply to this. So we really have kind of run out of options here. This does not fit the form of any type of algebraic technique that we've learned before, which means that if we wanted to get the value of this integral, we really would have no choice. We would have to go a numerical integration route. I would leave that for you to do. And again, in the homework, you will see many examples of functions where you will have to do the midpoint, the trapezoid, and Simpson's rule.